Hello, everyone. My name is Chelsea Swoopes, and I'm excited to present our work on supporting sense-making of large language model outputs at scale. This work was done in collaboration with Katy, Gero, Ziwei, Jonathan Kummerfeld, and Elena Glassman. Okay, so large language models are capable of generating multiple different responses to a single prompt. With OpenAI's ChatGPT, a user can regenerate a response. Similarly, with Anthropic's Claude interface, users can press retry, which will generate another response to the user's query. And then lastly, we have ChainForge, a work that will also appear at Chi 24, which is designed to allow users to generate multiple responses to a single query simultaneously. We conducted a formative study with a domain expert, multiple system designers, model characterizers, and model auditors who were engaged in an iterative inspection of LLM responses. We found that users typically engage in iterative inspection by using a chat interface, which is often slow, or by pasting these responses into a spreadsheet and analyzing the responses row by row. They reported sense-making and making decisions about model and prompt selection at the scale of tens to 100s of LLM responses. This scale is greater than the inspection of one or two outputs at a time, as is common in like a chat or playground type environment, but it's less than the many thousands of outputs typically involved with annotation studies. And so we therefore call this the metal scale or the middle scale of LLM response sense-making. So who generates multiple responses and why? Well, users may want to select the best option from among many. They may want to compose their own responses through bricolage, consider many ideas during ideation, compare the functionality of different models or prompts, or audit a model by looking at the variety of possible responses. Sense-making of many LLM responses is necessary for various tasks, and it requires inspection of outputs at different scales. In this work, we aim to support the inspection of outputs at what we define the mesoscale, which is tens to 100s of LLM responses. In this work, we're interested in rendering text from language models, and we want to do this for sense-making of LLM responses at the mesoscale. So we will examine some existing bodies of research and development, focusing on interfaces tailored for sense-making. This overview will help contextualize our work within the broader scope of sense-making interfaces. So first we see sense-making interfaces for cross-document text visualization. These three images show how SentiTree abstracts away documents as nodes within a graph, and TopicLens and ContraViz abstract away documents as a dot on a 2D plane. These are lossy document representations, so a user could not take this output and reconstruct the original document. Related work can also be found in the space of rendering code corpora. So for example, we have overcode, which pre-computes and renders sub and cross-document relationships using visual text attributes and spatial layout. And as we can see, it dims code that is similar and makes apparent code that is different. And we build upon this feature with natural language. Okay, and then we have work that creates diagrams to connect concepts. We have Sensescape, which was designed to support complex information tasks with an LLM by enabling users to manage the complexity of information through multi-level abstraction. And then we have Grapholog, which converts responses to graphical dialogues. These help transform long and complex LLM responses into diagrams that connect the concepts in the response using a graph. They enhance the rendering of individual LLM responses rather than rendering the distribution over possible LLM responses to the same query. And so they do not explicitly address the stochastic nature of LLMs. And lastly, we have interfaces that support automatic evaluation of prompts. Here we have PromptFoo, which was developed for prompt engineering and evaluating prompts against predefined test cases. Automatic quality measures require that you already know what you're looking for and have a predefined goal. So this prompt food has some cross-document support for comparison, but it's only between pairs in this interface. And we're thinking about the many-to-many relationships that, the user does not know yet. It emerges from the data. And so therefore we cannot write automatic quality measures for them. And so in our formative interviews, all interviewees said that automatic evaluations were not useful when it came to developing LLM applications. Several interviewees had explicitly investigated if benchmarking evaluations of LLMs correlated with which model worked best for their use case, and they found no correlation. And so because automatic evaluations could not predict success at their task, all interviewees engaged in some kind of manual inspection for evaluation. Okay, so in this work, we wanted to design text rendering techniques to support sense making of LLMs at the mesoscale. We developed on work that is appearing this year at CHI, the ChainForge open source visual programming environment. On the left is ChainForge's prompt node, where users can enter their prompt. They can choose the number of responses they want generated, and they can select which model or models they want to query. Users can add as many models as they'd like. Here we only are showing 2. On the right side is our grid inspect node. This has our text rendering techniques or features for sense making of LLM responses at the mesoscale. This first feature is exact matches. This feature enables users to see how similar responses are by finding and identifying exact matches across responses. And so we detect and highlight the longest common substring. The hypothesized benefit of this feature is that users can shift cognitive bandwidth from recognizing overlapping language to answering more complicated questions. And it also gives a skimmable sense of literal repeating patterns across all the responses. And so here you can see that we have callouts of exact matches within model responses, and also across the model responses. Next, we have unique words. This feature it highlights words that are unique to a particular response. And so it indicates that other responses are unlikely to contain that word. And we hypothesize that this feature will allow users to see what is distinctive about responses. Next, we have positional diction clustering, or PDC. This novel algorithm is designed to identify any emergent structure and variation within that structure in a set of LLM responses by finding sets of sentences across different responses that are similar in diction, so textual content, and position. Here we can see that it's highlighting analogous text across LLM responses. So sentences that are positionally consistent and similar in diction are highlighted in the same color. We hypothesize that this will allow users to see emergent relationships. PDC can be rendered in 2 ways. One way is in a grid as shown here, where responses are side by side. Lastly, we have a novel rendering of the PDC output, and this feature is called the interleaved view of positional diction clustering, which is the second way to view PDC. Here, users can see the sentences one by one, ordered by their similarity. So words that are gray exactly match the words above them, which shows users repetition of responses. The groups are ordered approximately the same as how they are in the responses. So for this email rewriting output, we see the greetings and the subjects at the top. And at the bottom, we see all of the thank yous and closings. We hypothesize that this rendering will be useful for users who wish to remix parts of several different LLM responses. We also think it will support the identification of rare response components, as they will be easily identified as singleton groups. And lastly, it will support characterizing the complete distribution of LLM responses, since the volume of screen real estate taken up by any given group is proportional to the number of responses that include a sentence in that group. Okay, so to evaluate our features, we conducted an in-lab controlled study with 24 participants who completed an email rewriting and model comparison task. And we also conducted an unstructured case study with 8 remote participants who were interested in using our interface to understand and examine LLM outputs in their own work. Participants for the case study brought in a diverse range of tasks, such as generating character voices for creative writing, prompt engineering for journalistic feedback, generating business ideas for business forecasting, and identifying trademark confusion for legal research. They requested for the model or models to generate anywhere from 20 to 100 responses per prompt, and the generated responses were between 50 to 500 words. Okay, so going into our findings, we found that exact matches helped participants identify how consistent or diverse a set of responses is. They used unique words as an extractive summary of a response. Grid PDC was used to determine consistency or uniqueness across groups of responses, and they used interleaved PDC to identify smaller variations within a cluster of similar sentences. We also found that there was variance across user attitudes, tasks, and the desired number and length of responses. Some users were hesitant to increase the number of generated responses as they initially assumed that it would be too overwhelming. Next, we noticed that task stage and user preferences impacted how many responses participants wanted to view at once. And so this is typically a reflection of the user's information processing style. And then lastly, some participants wanted to look at paragraphs, others wanted to review fragments of sentences, or even output that was returned as a JSON array. These different response attributes require algorithms to be more adaptive. Okay, so in closing, the existing and novel features we designed can support sensemaking of LLM responses at the mesoscale. We developed a novel algorithm, positional diction clustering, or PDC, which can be viewed in a grid, side by side, or interleaved, which is our novel rendering of the PDC output. PDC was helpful for a variety of tasks, and it was often the most popular feature among our participants. Tasks that were previously either done via brute force or considered too difficult to attempt were now deemed as tractable. In addition to the features we provided, users would suggest additional features tailored to their task, which indicates the need for additional algorithms and renderings. So you can see more details on that in our paper. As LLMs are increasingly adopted, supporting end users, system developers, and system examiners in making sense of the stochastic capabilities of LLMs becomes an increasingly important area of study. And this work presents that support for those making sense of LLMs at the mesoscale. Thank you. We hope to incorporate this node into the ChainForge visual programming environment and release an open source version of PDC. If you wish, you can explore with the research version at the link here, which is language-play.com/mesotext. Thank you.